In Chapter 9, we're going to use overlap graphs to create a sequence assembly, and we'll do that using shared k-mers. So we're combining a few things that we've learned before to create a graph structure, which if we look at the Rosalind graph challenge here, we can see some nice background on graph theory. Very much fun stuff to read about, learn about directed graphs, which I'll talk a little bit about. And I encourage you to read all this, but the heart of this is that we're going to be given a FASTA file, which we have now seen before, and we will parse this and we will find where the end of one sequence, for instance the 3 A's here, overlap with the beginning of this sequence here, and we're going to do that programmatically so that we can do this for any number of sequences. So given this sample data set, we see that 498 can be joined to 2391, 498 to 2391, and I will note here that the order does not matter. You can print these in any order, it will be fine. And then we see here that 498 can also be joined to 442. And finally, 2391 ends in TTT, and therefore it can be joined to 2323 on the first 3 T's here. So that is what we're going to be creating here. The exercise, the Rosalind exercise, only asks us to join just pairs of sequences. You can extend this into all the sequences that overlap, and you will start creating longer contiguous sequences, which are often called contigs, and you could extend this logically even to whole genomes. So this is the basis of it is a very simple idea for a genome assembler, which we often use when we have short reads and we're trying to assemble them into longer genomes, or at least regions that we can look for, for instance, coding regions. So we only need to join 2 sequences to pass the test, but I am going to show you how to go ahead and create a full assembler using very simple overlapping rules. And some of the things that we're going to learn here is how we can use k-mers that we've used a couple times now to create those overlap graphs. I'm going to further introduce the idea of logging runtime messages to a file, which we have not done yet. We're going to be using the logging module for that. We are going to come back to default dict. We use that in the counting chapter, and I'm going to show you how to use this for lists. To find things that are the overlaps, things that are common in between 2 collections, we're going to use sets, and how sets have a function called intersection to find the common elements between them. We're going to use product from the itertools module. We've used a few functions from there. Product will give us the Cartesian product of 2 lists, which we'll need. And then I've mentioned star map before. We're going to show you how to use star filter to write some pretty clever code. And finally, we're going to use the GraphViz tool to both model our full genome assembly, our full sequence assembly, and also to visualize that for us. And I think that's pretty fun. So to get started, you should start in the main directory here of the GitHub. Make sure you do source v&v bin activate so that we have our virtual environment activated. I'm going to do that in 2 windows. I'm going to go into the 09 graph directory. And to get started, I'm going to copy the solution 1 to a program called grph.py, and I'm going to run make test and see what all it has to do. So we see that this version does pass, and what does it expect? Because as with many of the other challenges, I'm going to encourage you to write this yourself before you look at my answer. Not a requirement, but I think that you should. So it requires 1 positional argument, which is a FASTA file, and then there are 2 options. One is for the overlap size, which I'm going to call the short version. The short flag is going to be called K, which I think for most bioinformatics users, they would think k-mers. So the size, the choice of K for the short flag is intentional, but -- overlap is or overlap size is probably a more thorough explanation. And then finally, a kind of, and we see here that the default is going to be 3. It's not actually a requirement of the Rosalind problem to have a varying overlap size. It defaults, it's hard-coded to 3, but there's no reason for that to be hard-coded, so I'm going to show you how to make it variable. And the other thing is we have a flag here that for the first time we're seeing is a Boolean flag. You see here that K takes something that is a size and overlap takes something that is a size, but debug, it does not take an argument after. It's either present or it's not. And so often this is called a flag, and usually the way flags work is that the meaning is true when it's present and false when it's not present. So when we do not have the -d or --debug flag, then we don't want debugging, but when we have it on the command line, then we do want debugging. And we will see what that means. So let's look at the first input, which is the exact same as what is on the Rosalind page, and we see it is a FASTA file that we need to parse, and so I hope in your mind you go straight to thinking, well, I will use bioseq for that. So if we run this, if we run our graph program on that input, we see the output that we expect from Rosalind. And so that is why this passes, and here's a nice visualization of the 3 sequences, sequence pairs that can be overlapped on 3mers. We see that these overlap on 3 A's, 3 T's, and 3 A's. If we increase that to 4, then only 2 sequences can be joined. And so let's run that with a K of 4. And something to note here about the way that argparse handles arguments on the command line is that the options here can come at the end. It's not a requirement that they come before positional arguments. Some argument parsers, it does matter. So argparse is pretty flexible that way. So I could have run it like this with the -k before the positional arguments. So the last one is that there is a --debug option, and let's look at what that does. I'll just run it with the short flag here, -d, and it doesn't appear to have done anything different, but there is now a file called .log here, and we see here that 5:46, that is my current time. We see that that is when this file was created, and if we cat that file, I see that there's some interesting output here, and I'm not explaining what this output is yet, but just the fact that it is now present is kind of cool, and it was not there. If I run this again without the -d and I cat that file, you see it's empty. So the file is actually created every time the program is run, the way that I've written this right now, and it's simply overwritten with no output when you don't have debug on. So that is what is going on. I will also, I mentioned here that the flag can come at the end or it can come before the positional arguments, and that's just the way argparse works, and it's fine. So if you think you know enough, you could figure this out, I would encourage you to stop the video and go write a solution yourself. If you want to see me work through this, then I would encourage you to stick with me here. So I'm going to start over with new PY and look at what I have here for graph. And the first thing I want to do is change my arguments to match what I saw on the command line. And so we're going to take three arguments. One is going to be a file. I think I call it file, yep. And one is going to be, there's already an integer thing here, I'm going to call it K, and then debug. And I would point out, perhaps K is a terrible name. It is such a common it's perhaps terrible because it's a single letter, but it is a very indicative letter in bioinformatics where we talk so much about k-mers, which the idea comes from, I think it was first originated in linguistics where they call them n-grams. So, perhaps N is an even worse slot name here. But because we talk so much about k-mers, I think most people would think K is some sort of a size. But you're totally welcome to use a much longer, more descriptive name here. So K is going to be an int. And then I have already here, there's a Boolean argument here, and I'm going to call it debug. So that is why I've given you an args, default args structure that has these examples, just so that you can remember how to create these things. So there's a little bit here to type. I'm just going to copy and paste these bits. Let's see. I'm just going to go ahead and get rid of all of these parts, and I'll just paste these in one by one so we can talk about them. So this is the way that we create a file argument. And again, because I'm going to point out that argparse file type has technically been deprecated, and I appreciate that, but I wrote the book before it was deprecated, and so I'm going to continue to show how to use this. It still works, and I will probably have an addendum at the end that explains how to not use this. But since I'm just explaining the way the book as it's written, we're just going to go ahead and continue using this. And let's see if I can. I was trying to run my formatter, and kind of made a mess there. So I will format this at the end here. So I'm creating a file argument. It is positional because it does not start with any dashes. And additionally, I'm just going to go over here. It'd be easier if I just open my solution 1 and copy this, the get args. No reason to make my life harder. So I'm just going to paste this. So there is my first argument, positional argument. It's a file. It's going to be reading the text. Very important that you either do not give an argument here, it will default to reading text, or that if you put something there, you make sure that you put R for read and not W for write, because then you will actually overwrite your input file, which is a mistake that I've made before and is terrible, because then you have to recreate your input data. Then we have here, we are using the type of int. We've seen before how much. So if you use the type int, it will save you a lot of effort in validating your data, and K will actually be an integer value already converted from a string for you. And additionally, we can use a default value of 3 here, so that the user is not required to put anything at all. That user will probably be you, so you should always be looking to make your life easier. And finally, we have, this is a reason why I wrote NewPy is that I had trouble remembering how to create a flag. And the way that argparse does it is that you define your short and long. You can have one or the other. It's an optional argument. I have a help, and the only other thing it needs here is the action, which is store true. There is also, there are other actions. One is store false, so we'd actually invert the meaning. So when I say store true, that means that when this is present, it will put a true value in here. Therefore, I don't actually need to put a default. The default is going to be the opposite of true, which is false. So that is how I get that to work. I'm going to go over here, and one other thing that I need to do is to actually, as swell as it is that that argparse will do all of this work for me to at least ensure that K is an integer, I'm not able to say that K needs to be a positive integer. So after argparse has done its work, I'm going to do a manual test here, and I'll say if the overlap, and it's called overlap because argparse uses the name of the long flag for the slot. So I'll say if arg's overlap is less than 1, then I'm going to use my parser error that I've used before with a nice informative error message that says -k, and then I will show the value of args overlap, and I'll say it must be greater than 0. And with that, I can return file is equal to args.file, k is equal to args.overlap, and debug is equal to args.debug. I show here in the book just using a positional arguments here, which line up with the way that the slots have been defined for the args, but it really is safer to do the full using the named arguments here. So I will continue to demonstrate that. So always a good idea here to just get started, print args. Let's make sure that our program works. So it's called graph. I will run this. I will run -h. That all looks just exactly the way I want. I'm going to do test inputs 1.fa, and when I print this, I see something that looks gross. A file is equal to this text.io wrapper. Okay, that's kind of ugly to look at, but I can see that the name of it is the input file that I gave, and then I see k is equal to 3, and I didn't set it, so it's using the default, and debug is equal to false because I didn't set it. If I change that to -d, then I see now debug is true. If I change this k to 4, I can see now k is equal to 4. So I am reasonably happy with the way my program is going so far. So my next step is to, I have here a suggestion to run PyTest. Why not? Let's see how well we're doing so far. As usual, we're going to pass the first couple of tests just by having a file that exists with the right name. It has usage. It actually is testing bad k. So let's give that a shot. If I run this with a k of 0, and I can actually give anything here, can't open foo. I can't actually give anything. I need to say test inputs 1. It needs to be an actual file that opens. Here I see that it's blowing up because k is greater than needs to be greater than 0. So that was one of the tests that we saw that was passing. And we're getting that passing test because we're doing a little bit of checking there in with the parser error message. And then we're also passing the test for a bad file, which I also just showed here. When I said run on foo as the input, what happened was that argparse file type saw that that wasn't a file that it could read, and so it created a very, very nice error message telling me exactly what the problem is. There's no such file or directory called foo. So I want to introduce how we can manage the runtime messages that we create with using 3 ideas: STDOUT, STDERR, and logging. And I've mentioned a little bit before about STDOUT and STDERR, and so I have a program here in the root directory called log that you can look at, and it shows you a very basic style of logging that you could use very effectively. Most of the time I can get by with just printing messages to STDOUT and STDERR and segregating them with command line redirection, and it's generally good enough. But there are times when you want something much more powerful, and for that we're going to use logging. So this program is demonstrating that when I do a normal print without any other arguments, and I say this is STDOUT, that's where this is going to end up. I can be explicit about it, and I can say file is equal to sys.STDOUT, and for this I need to import the sys module. And to print to STDERR, I need to change file to sys.STDERR. And if I run this, all 3 lines appear on the command line. So if I run log, I can see all 3 lines, but there's something very subtle going on here. This standard error is actually just showing up still on the console because I haven't told it to go anywhere else. And so I can actually redirect both of these, STDOUT and STDERR, to different files. So I can say 1, which is the file handle for STDOUT, is going to go to something called out, and 2 is going to go to something called error. And now I see nothing on the command line, but if I cat the out file, I see there are 2 lines, the ones that were printed to STDOUT, and if I cat the error file, I see that's the STDERR. And now, if you consider what we are often doing in bioinformatics, which is churning through enormous files and trying to look for, we're trying to find some error. If we're going through literally millions of lines and there's only like 3 errors in there, we don't want a million lines of output that we then have to search through to find the problems. We could only print the errors to standard error and segregate those so that we then end up with a file that only has the lines that we need to look at to fix the problems. And so this will often get you what you need. But let me show you about the logging module, which is very, very handy. And for this, I'm going to go import logging up here. And I'm going to bring in these 3 lines of code here, or these couple lines of code here, well, actually, let me just go get this from my solution 1. And because then the formatting will be correct. There we go. All right, so I've now brought in these lines of code. The way that the logging module is that it works is that it basically works globally. So as soon as main starts, I'm going to call logging basic config, a function that's in the logging module, and I'm going to give it some parameters about how the logging will work for the rest of the program. I'm telling it that it's going to create a file name called .log, and this is hard-coded here. You could, of course, make this an argument to your program or do this however you want. The file mode is going to be W, which means every time this runs, it's going to open that file in the W mode, which is the same mode that we're looking at here. It's the same mode for open, and so that means the file will be overwritten every time. You could open it in A mode for append, but then the file would grow and grow every time you run this, and there's a reason why I call it .log. It's because I don't want to see it by default. It's going to be a .dot file. And so you wouldn't normally see it unless you do ls-la. Let's look at that real quick. So if I say ls real quick, I see here I don't see .log. I have to do ls-la. And then when I look here, I see that there is a .log, and right now it's 0 length because it just got overwritten with no output. And so this, if you were to change that to A, this file would grow and grow every single time you ran the program. And because you don't normally see it, you might end up, for instance, using all your disk space. And then you'd be wondering, why is this happening to me? And you'd have to remember that this file is there. So could be dangerous to start this in A mode, but sometimes you might want to. And then this last one sets the level of debugging. And so in the logging module, there is, and I'll jump ahead here, there is this little table here that shows of the logging modules going from critical down to not set. Not set's actually kind of weird, but debugging is down here at this level of 10, and critical is this higher level of 50. So this is a way of saying, I want everything that is from the range critical on down, or I only care about debugging messages. So we're only going to worry about two levels here, critical and debug, and that relates to this table here. If you want to learn more about the logging logging, you can go into the REPL and you can import logging, and then say help on logging. And there's a lot of things here that you could read, or there's the online documentation. I have a link to that. Lots to learn about logging, but we're going to use it just very simply here. A note here about the dot files. They are normally hidden from view. And so I have here that you have to use the -A option to see them. There's another critical file that is in this root directory called .gitignore. And if I look at that, we'll see here that the .log file is in it. And so this is an important file for Git, as you can imagine. It is a list of file names or file patterns that should be ignored when we're doing commits and adds. So if I were to do a git add -A in this directory, it would by default want to add my .log file. And that would be bad for many reasons. First off, that log file could get very, very large, and I don't want to commit large files to GitHub. They get very upset. You should not put sequence files in there, large sequence files. You can put small test files in there, but you can't put gigabyte size files into GitHub. And so I never want to submit my .log file. Very common, I'll have a .env file that has maybe passwords, connection information for a database. I don't want that information to be made public, so I put it in a .env file, and then I make sure that that file name is in my .gitignore file. I don't want to, for instance, commit the name of the solution here because I in my GitHub repository I only want my solution, the ones that actually have solution in the file name. I don't want to add any of these other files, like the output file that I just demonstrated in the error file, and these are some output files from other runs of the program that I'll be using. So I don't want any of this to go into GitHub, and that is what .gitignore is. And so that is actually already in your directory, and you don't have to add that. But it's very important for you to know about. For instance, it's very common for me to create a data directory in a project, and I'll put all my data in there so that my .gitignore file will just have data, and I'd say don't add the data directory. Very, very important for managing your GitHub repository. So with that, if we run this program now, and we run this with debug on, then we can cat the .log file, and we see that there is something there. And if we run this without debug, and we cat the log file, we see it's empty, which is great. The way that this is being printed is this older style of kind of it looks almost like printf here, where here the placeholder is this %s symbol, and instead of the curly brackets that we've been using with format strings. And so this is it's really an older way in Python to do the variable interpolation inside of a string. And at the time of the writing of this book a few years ago, this was the preferred way of doing it. It may be different now. You can put f strings in there. I'll be showing that here in a minute. So a point here about the debug is and the logging is that when you are doing if you're just printing to standard out and standard error, you have to be there somehow in running the program, either manually or when you are typing this out in a shell script to run your program. You have to manually figure out the one redirecting to some file name that you're going to give it, and two redirecting to some other error file, and that can be cumbersome. And so if you use this if these become command line arguments now, or you can build that logic into your Python, and rather than try to put it into a shell script, it becomes a lot easier to handle your logging programmatically. So if you're debugging on your laptop or some server that you have access to, you can have debugging on. But then when you deploy it to something like your HPC cluster, then you can turn logging off by just not passing the debug flag. And especially when you're running on an HPC cluster, you might be running in parallel, and so each job is going to want to have its log files written to a certain log name so that you can separate out what problems you had with which jobs, and all that can be rather cumbersome to deal with in writing shell scripts. So logging can be a lot easier way of both figuring out where to write the files, but also just completely turning it off. If you don't use logging and you have all these print statements and you suddenly don't want to see any of them, then if you're just using print statements, you have to go through your code and find all of them and comment them out. whereas if you're using logging, you can just turn them off with one flag at the top. So with all of that, let's move forward into finding overlaps. And I'm going to read a FASTA file, and there's no point in parsing that myself. I certainly could, and you probably should at some point write a FASTA parser, but I'm not going to worry about that for right now. I'm going to use this very, very handy code, and I'm going to put it after my logging. I'm going to leave the logging in place. And I'm going to say for rec in seek.io parse, I'm passing it the args.file, which has already been opened for me by argparse and validated that the file exists. We have not validated that it's actually FASTA format, and so that's actually going to happen here. If I try to parse something that's in FASTQ format or just not a sequence file at all, maybe some sort of a PNG that I passed, then seek.io parse is going to fail. And so that's another level of protection that we have that we're dealing with well-formatted data. And to get started, I just want to print the record ID and the record sequence so that I can see, first off, is my program working? And what does the output look like? So with that, I'm going to run graph on tests inputs 1. And I see the expected output. I see the record ID, and if I again cat my input, there's the record ID, Rosalind 498, and then there's the sequence AAAT, AAA, and on down for all of the sequences. So I am easily parsing my FASTA input. Important here, I have a little note, just really want to stress that you only write 1 or 2 lines of code and then run your program, then run your tests. Repeatedly try to break your program and then get it to work. Do not write 40 or 50 lines of code and then run your program. That will not work out. Try to only change one thing at a time if you can. So with that, I would like for you, from this point, I've kind of set you up with all the tools that you need here to get the inputs, validate your inputs, and then set up some logging if you want, and then to parse through the input data. And from here, I'd like to challenge you to first create something like this, that the first, taking this sequence now, we're already printing this part, I'd like you to print the first 3 letters, which is AAA, and then the last 3 letters of each sequence, AAA, for each one of these sequences. And think about how when the last 3 are the same as the first 3, so these 2 sequences could be joined. They overlap here and here. So once you have that working, change the value to 4 and then look at what sequences have an overlap. We see there are 4 T's here and 4 T's here, and so those 2 could be joined as well. And see if you can at least get this much to work. I encourage you just to stop the video and to get that much working, and I'm just going to keep moving on here. So as I'm going through this, if I'm printing this out, at the point that I printed this line, I have no information about what other sequences it could be joined to. Even at this point, I do have some information that this could be joined to this, but it could possibly be joined to something else. I see this last 3 could also be joined to this 3. So I'm going to have to somehow store all the information about the overlaps and then go back at the end and figure out which sequences can be joined. And this gets at a key part about about assembly, is that we often have to use data structures that store basically all of the data. So if you're dealing with, a human genome and you're dealing with about 3 gigabytes of input, you're going to have at least 3 gigabytes of memory available to you. And that's generally not a problem in a lot of bioinformatics. A lot of times our machines are big enough and our genomes are small enough. But if you have 50 human genomes in a file, all of a sudden you may not have that much memory, especially like on your laptop. So we have to think about data structures that will fit into memory. And even though Python is not a language that we often use for high performance, a lot of high performance computing, and a lot of the reason is because we don't have that much control over how memory gets used. We can still be careful about how we use Python to make sure that we're not using more memory than we need. I'm actually going to show you kind of a wasteful way of storing this because it's simple, but we could talk about how to make it, how to use less memory. Okay, so a point here about the way that we could store this information. So first off, here is how we could, how I can store this information. I'm going to use two dictionaries. One that has all the sequences grouped together by the start sequence that I'm using, and a separate one for all the end regions. And I'm going to start off with, the keys are going to be arcade length subsequences. When k is 3, it's going to be AAA, for instance. And the values are going to be a list of the sequence IDs that have that region. And so I can use k in my code. I'll use the REPL here. K is equal to 3, and I can say my sequence is equal to that first sequence, 3 A's and then 4 T's. And I can say, what is the sequence up to k? That's my first k-mer. And my sequence starting negative k to the end is my, I don't need the 3. Starting negative k to the end is the last 3 letters. So that is a very simple way of using string slicing to get the first k-mer and the last k-mer in my sequences. That is certainly a very good way to start off that will help you print this bit here that I suggested. So rather than just printing them, though, I want to store them into some sort of a structure. And because I'm getting the k-mers, I could very easily use this code in my function in my program, but I'm going to actually step back and write a function to find the k-mers in a given sequence. And because I've done this a few times now, I think it's time to write a function for this. And so I'm going to call it find k-mers, and I'm going to start off by returning the empty list. So in creating this function, and by using some type hints, it really helps solidify what it is I expect from this function. Given a sequence that is a string and some size of k that is an integer, I want a list of the strings back that are that size. I have a nice doc string here, find the k-mers in a string, and I'm going to start off by returning the empty list. And I have here a decent test for my function, a decent unit test. I will put this in here. And so given the empty string and some value of k of 1, I'm going to get back the empty list. Again, it is up to you how you might choose to throw an exception on an empty string. I don't like exceptions, so I never use them. In my case, I just choose to return nothing. When I have a string of ACTG with a k of 1, I'm going to get back the individual bases of the sequence. For 2, I start to get these overlaps of AC, CT, and TG. For 3, I get 2 k-mers. For 4, I get the entire string. And when k is greater than the size of the input string, I'm also going to return the empty list. That could, depending on how you go about writing this test right here, the first and the last might actually break your code, because if you were doing some sort of a trying to get at data that doesn't exist, in a way Python is a little easy about this in a way that makes me uncomfortable. In some languages, if you were to try to access a slice of something where it doesn't exist, it would create an exception or some kind of a reading into memory you don't own. But Python is kind of easy about this in a way I don't love. But so I would encourage you to stop and write the function that passes this unit test. And if you're continuing on with me, the first thing here I'm going to write here. Oh, well, before I actually run that, let me go here and run PyTest on my graph program, and I will ensure first off, okay, it's not happy with the fact that I'm talking about list, and I haven't brought that in, so I'm going to go up here and put list here, and then I'm going to run this again. And what we see here is that my function is in fact failing. This is the point of test-driven development. I've written a function, I've written a test for that function, and right now the function doesn't work, and I assure myself that my test does fail. So it helps me know that my function is wrong. So let's correct the function. The first thing to do is to use this formula to find the number of k-mers that I have. So the n here, a terrible name, but n does mean number, and it's the scope of this variable is only going to be inside of this very, very short function, and so I think it's an okay variable name in this instance. And I'm going to use an if expression, which we've seen before. If n is less than 1, I'm just going to return the empty list. Else I'm going to use this little bit of code I've used a couple times before to extract the k-mers from the sequence. So this is the way I'm making sure that that I'm always returning something, the empty list. And note here that n is going to be 0 when k is greater than the length of the sequence. So I will never get into the problem of reading data or creating the wrong size k-mers. Like if the k-mer length is greater than the length of the sequence. So with that, I now have something that should work. I will run my test. I like to run with the -v flag, and I see that find k-mers is working. So I'm happy with that. Now I can actually just run find k-mers on my each input sequence, and I can use the 0 position for the first k-mer and -1 for the last one. I will note here that in this in this version, I have to set aside temporarily enough memory to get all the k-mers from this string. Normally, if we're dealing with short reads that are 1, 200, 500 base pairs long, that's not a big deal. If these were quite long sequences, then, you know, you could argue I'm really using more memory than I need because I don't need all the k-mers, I just need the first one and the last one. And I showed you how to get that. Pardon me. I showed you how to get that just using string slicing. So it could be argued that my find k-mers function is overkill, and I appreciate that. One of the things that I'm trying to do here is to show you how to write a nice little function and write a nice little test for it, and then to use that in your code. But I will say that from a performance standpoint, it would probably be better to simply slice off the first k-mer and the last k-mer using a string slice. So to go forward, how can I collect these into those dictionaries that I talked about? What I want is this structure that and if we run solution 1 on tests inputs 1.fa, and then we look at the .log file. Sorry, I need to turn on debug. What we see here is what I've created here is a dictionary that has the k-mer AAA, and all of this is the starts here. These are the 3 sequences that start with AAA, and we see here these are the sequences that end with AAA. So what I have here is a key. The string is a key, and the value here is a list of strings. So how can I create a data structure that goes from a string to a list of strings? And you could easily just use a dictionary, and going back to chapter 1, I show how to instantiate a dictionary using integer value of 0 so that we can count all the bases in a string. And then I ended up showing you how to use default dict with the type of int, and so that we didn't have to bother to see, does the key exist, do I need to initialize it to 0. We just were able to talk about the key in the dictionary and just simply add to it. We can do the exact same thing by using default dict, but with a type of list, and I'm showing that here, default dict list. And so to bring that into my program, I'm going to first off from collections import default dict, and I'll go down here, and before I start going through this, I'll say my start is equal to default dict of a list, and my end is equal to default dict of a list. So the first thing I can do is I can say if k-mers. So one of the things about using my find k-mers function is that if I am trying to find, for instance, k-mers that are too large for the given sequence, find k-mers is going to simply return no k-mers. And so it could be argued that that right there is worth the effort of using this function because it'll skip over sequences that are too short, and it does a lot of work for me, as opposed to the manual slicing of the list. So what I'm saying here is, and let's just start off by baby steps here. I will print start and end real quick, and let's just look at we've added one bit. Let's test inputs 1 and see what we have here. So we see here I'm printing the default, printing the start and the end, and what it looks like is not a dictionary, but it's saying it's a default dict, and it has a class of list. And so that's what's going on here. When we were doing the counting, I think we called that count, and we said it was a default dict that had an int in it. And then we were able to say something like count at a plus equal 1, and we were able to just default, it just created a for us when it didn't exist, and it created it with a default value for integer, which was 0. So therefore it was easy to add 1 to 0 and get 1. In this case, we're starting off with a list, and the value in here is it's going to be an empty list, which means that we can append to that list without having to instantiate it. So let's instead of printing those, let's print find k-mers of rec.seq for args.k. And let's see what that looks like. So we see now for 498 it has this sequence, and therefore we see that it has these k-mers, AAA, AAT, and on down the line. That is useful. So what I'm saying here is I could assign that to a variable. I could call it k-mers is equal to find k-mers, and then I could say print k-mers, and that will work. But what if k-mers doesn't exist? So I could say if k-mers, then print this. And we see it's going to still work, but if I go run this with k is equal to 10, then I'm going to print nothing, right? Because my sequences are shorter than 10, and k of 10 is actually quite short. A lot of times when we're doing overlaps, we want, say, something in the range of 20 to maybe 30. And so that's not an unreasonable value of k. So I can actually combine this into one line of code by using the walrus operator, which I've seen before. And so that's what's going on here. And if I change it back to 3, then I see I'm getting output. So if there are k-mers, if I'm able to find k-mers, so if find k-mers returns something and puts it into k-mers, and then the if says if k-mers, then we go execute the next line of code. So that is what is going on. That's called the walrus operators. If k-mers, it gets something from find k-mers, then I'm actually, instead of printing them, I want to take the first Kmer and use that as the key into my start dictionary, and then the last Kmer and use that as the key into my end dictionary, and I want to append these values. The values of the record ID is what I need. So with that, I can change my code to, instead of printing, the start and then the end gets the last one. And now let's print start and we'll print end. And we'll see how they change over the course of the program. And we see that took a little bit longer to run, but at the start they're empty, and then by the end they now have some data in them. You notice that they're kind of, this is hard to read, the way this is just, if I just print, it's kind of gross, and I've showed this before, and I introduced something called pprint for pretty print, and there's a module inside of Python called pprint. And it's pretty easy to use. We just import pprint, and instead of print, we use pprint. But we are trying to get away from printing. We're trying to play around with using logging. And so I want to, instead of printing this output, I want to log using logging.debug. And I'm going to print this big word starts with a new line. And then instead of pprint, because pprint would automatically put the output out there, instead I'm going to use it from the pprint module, a function called pformat, which will create that pretty string for me. And I'm going to pass it the start variable here so that it will actually print to my logging module, to my logging file, a nicer version of this. And I'm going to use this instead of printing to the end. I'm going to get rid of this print here because I don't need that. And finally, to use this, I need to go up here and from the pprint module, import the pformat function that I'm using. So with that, let's run our program again. And now if we cat our .log file, oh, I need to run it with debug, sorry about that. And now we see we have some pretty cool output into our log file. It's much easier to see, to read, and I only get this output if I run it with the -d flag. So all of that, really pretty cool stuff. You now have the information you need to create the overlaps. You can go through, and I encourage you to stop at this point and go through and find all of the sequences. Actually, I think that there's a problem here. I think I need to stringify the sequence real quick. Let's see. Let me do this. I think I want to pass string of the sequence. I think that will look nicer. Run that. Yes. I just want see, these are actually seq objects, and I want them to just be actual sequence strings. So what I'm doing here is I'm coercing the rec.seq, and if you remember, the record it actually returns in the seq slot is this seq object, and then we can do really handy things on that, like get the reverse complement of the sequence. It's actually this full-fledged object, and I want to coerce it into a string so that I just have the sequence itself. Now I have enough information here to know the overlap between AAA and from the end to the beginning. I would encourage you, again, stop the video and try to write the rest of the solution yourself. My first solution here is going to look at these two structures that we have and look for the shared sequences between the overlapped. So the keys that exist in both start and end, those are going to be the pairs of sequences that I'm going to create. So we've already gotten to this part, and I'm just going to show you the solution here that I came up with, and then we're going to talk about it for a while. So I say for the Kmer that is found, that is in the intersection between the start and the end. So this would be the shared keys. How do I go about finding the keys that are shared between two dictionaries? Well, I'm doing something called set intersection, and I'm going to explain that to you. I'm going to then say, give me the product of the k-mers between the end for that k-mer and the start for that k-mer. And you'll see here that, for instance, AAA, that is one that's going to be in common. And we see here that 498 occurs in both of them. And obviously I cannot join a sequence to itself, so I need a way of filtering out where these two IDs are the same. So I only want to join these these two pairs, 2391 to 498 and 442 to 498. So how do I determine which ones are not equal to each other? By using a function that already exists called operator not equal. And so for this, I'm importing the operator module, and I'm using the not equal. And then I'm using this other function here called star filter. It looks like filter, but it has star on the beginning. And I've already showed you star map, so perhaps you have an inkling of what this is doing. So it is somehow getting the product of these two lists, figuring out which ones are not equal to each other, and then that creates a pair of sequences that can be joined, and then I'm printing splat pair. This is all syntax that I've showed you before, so I hope you find it somewhat readable. Let me take you through how I came at this solution using many more lines of code to figure this out. So I'm not going to bother typing all this into the REPL. I'm just going to talk about how I use the REPL to get to this point. So all of this is I'm showing here that I'm importing some modules here, and one of the fun things here is that because I went to the trouble of creating my graph program, and inside of it is a find k-mers function, I'm just pointing out that in the REPL here I can import find k-mers directly from the function that I wrote. I don't have to type it into my REPL here to use it. That's pretty nice. This is all the code that I've already showed up to this point to instantiate our two default dicts and to go find the overlapping k-mers. So we have these two dictionaries now. So the first thing I started with was this very, very iterative approach where I say for each of the k-mers in the end, I say, is that k-mer in the start dictionary? If it is, I go through each of the sequence IDs in the end k-mer, and I say, is that sequence ID in the other start dictionary for this k-mer? And if the sequence ID that I have is not equal to the other one, then I print the seq ID and the other seq ID. That works. That gives me the answer. But it has this effect of creating this code that marches to the right. So I have 1, 2, 3, 4, 5 levels of indentation. 1, 2, 3, 3 for loops, 1, 2 if statements. So that's a lot of very, very manual typing to get at to finding these two overlaps. And so, you know, I wrote an ugly bit of code that passed the test. And always in any sort of creative act, the first job is to make something, is just to make something, and it can be terrible. You can just write some code, even if it is wrong. The act of going through writing it is helping you to understand the problem. And sometimes you just need to step away from the problem for a day, maybe go take a nap, and then come back, and it will help you look at your code, and then you'll be able to see the problems and how to fix it. So in this instance, I came up with a very brute force, ugly way of solving the problem, and I thought about it, and I said, well, what am I trying to do? Well, I'm trying to find essentially the intersection between two dictionaries. And if I take my start, I can actually, so let me go into my code here and show you that I can print the set of start here. And I'm just going to print it here so that I can run my program. So I'm running my graph program on tests inputs 1.fa. And this is what the set of start looks like. And I can put some information here. Start is equal to, and end is equal to the set of end. And when I run this now, I get just the keys to those, and in a way that they're unique. So the keys of a dictionary are already unique, but I've now further converted them into this thing called a set. And the reason for that is that I can now do an intersection. So I can say intersection set, let me make sure I get the order of operations right here. What I want is the intersection from the start to the end. So from the set of the start, that gives me an object that then has a function, a method attached to it called intersection that I can use to find the intersection of these two. So if I run that, I see that the intersection, this end has 4 keys, but the intersection of these is only 3 keys, GG, AA, and TTT. So the CCC here gets left out. So that is just a very clean, easy way to find the keys that are shared between 2 dictionaries. Now you do have to imagine like if these are enormous dictionaries with both of them with using a huge amount of memory, and now I have to copy those dictionaries into new data structures called sets, and then I have to have those 2 sets do the intersection. This may actually end up being a very poorly performing program given a very large data set. But again, it's probably better to just write something that works and then revisit it later when it turns out to be some sort of a problem. So this is definitely good enough for our solution, and it gets at, more importantly, it gets at this idea that there's already a function that exists that you can use, and because if you think about the thing that you're trying to solve intersection. There's no point in writing intersection code yourself. It already exists. So given these 2 lists, for instance, all of the sequences, let's run this with -d so I can look at our log file again. Given these lists, what I want is, given AAA, that it does exist in both, I want an intercept. I want some sort of a product, the product of these and this. And so I can actually demonstrate that to you in the REPL. Let me just pull up a new REPL here, jump into Python, and I'll say list 1, let's see, X, I'm going to call it just X for the moment, and Y is going to be equal to this list. So how do we create Y is equal to that? How do we create the product of these 2? Well, I'm going to import from itertools product, and I'm going to say what is the product of X and Y, and it's going to create this itertools product, which is hopefully you see that and you're immediately like, oh, that's a generator, that's a lazy function, and I can use list to coerce that. And so it's a little hard to see. Let me make this window bigger. And what it is a list of pairs. Let's just import, let's see, from pprint, import pprint. So we can pprint that list. And it's much easier to see now that this is pairs of strings. So X looks like this, Y looks like this, and this pairs up 498 with 498. And then it pairs up 2391 with 498. And then it pairs up 442 with 498. That is so cool. There's no reason for us to write a function to create the product of these 2 lists. We just import from itertools. We've got that. Now the question is, how do I filter out the ones that are the same? Well, I can use filter for this. So if I say filter, and I say, given a lambda, which is going to be a tuple, these are tuples, I want where T0 is not equal to T1. And I want to do that for, let's see, do I have it? Product of XY. And if I do that, I get a filter object. So, okay, I know I need to use list in the REPL here to coerce that. So now I only have 2391 to 4098 and 442 to 498. I no longer have the combination of the sequence to itself. And that totally works. But I just don't like this syntax. I think that's ugly. And so I did some searching when I was writing this, and I was like, you know, I found star map. Maybe I can find something for Python star filter. And when I searched for that, I found from the iteration utilities a function called star filter. Let's see. I did not activate my module. I did not go into my virtual environment, so I don't have this installed in it because I just started up a basic REPL. But I'm just going to go continue showing you here from the book that if I use star filter now, I can unpack the tuple into values A and B. And I can just say A is not equal to B, which is a cleaner way than writing this subscripting of a tuple. Here I called it P for pair, which is fine. This is a little nicer. I appreciate this. But it turns out, why am I writing A is not equal to B? That's actually an operator. And I'm showing here that I can import operator using an alias, just simply because I don't want this line to get too long. I'm going to shorten operator to just OP, op. Very, very often we talk about like a no-op operation. Something that's a no-op means there's no operation. So op is very commonly used to shorten operator. So if from the operator, if I import operator, then I can use the NE function, which is operator not equal. So now I can say star filter on not equal the pairs, which is a much cleaner way of writing this. And now I have exactly what I want, the Cartesian product where the pairs are not the same. I can iterate over that with a for loop, and I can use print splat pair. And so that's going to turn pair is going to be at this tuple. And if I were to print the tuple, it would print it with all this extra parentheses and commas around it. That's not what I want, the output of the program. It expects just the names themselves, so I can use the splat operator to coerce that into a list, and then the list is fed to print. Print uses its default separator of a single space, and it prints exactly what I want. So I could even shorten that down to this, but even I find that unreadable, so I would not recommend it. This is a pretty straightforward way of writing it. So if we go back and we look at this point, I'm just going to copy solution 1 to graph.py. That is what is going on in my graph program. And so for Kamer, in the intersection of these two, use star filter not equal on the product of those two and print the pair. And if we run our program, we find my other window here. And if I run pytest-xv, it passes all my tests. If I run make test, it's going to run a couple of extra. It's also going to do some flake 8 on it, which is great. So with that, we now have a solution that works. It passes our tests, and that is all you need to do. And in fact, you've already gone above and beyond for this challenge by introducing logging, which I hope that you find to just be a handy little skill that you can put in your back pocket to pull out whenever you need. I want to just take this a little farther, though, to show you how we can use a graph to find all of the ways that we could join the sequences. And to do that, I'm going to, well, first I'll show you that if we just extend the 3 letters that we're using right now to just find 2 pairs, then we can actually find a way to join 4 sequences together. So we start off here, the 3 A's starting here can be joined to the overlap of the end here, and then that could also be overlapped to 2391, and then that overlaps with 2323, and so we could create a much larger graph structure, and it actually turns out it's not very difficult to do. To do that, especially, I'm going to show you a picture of this, I'm going to install GraphViz. And so we don't need to install GraphViz just to create the graph structure, but we only need it to visualize the graph structure using something called the DOT language format. and I'm going to use a Python module that will write this format for me, and then I can use the GraphViz dot tool to visualize that. So really kind of reaching out into the ecosystem of other things that we can use. The solution 2 has all the same arguments for the solution 1, but it has an additional dash view object, a flag here as to whether or not to open the output file, the image that it creates for us, which is quite nice. And so if we run in here in the parent directory, there's a bin, it's called all test. What it's going to do is it's going to take as the argument here the name of the program that should be run, and it's going to take all of the programs in this directory that start with solution and copy them to the name of the program that I said, and then it's going to run the test suite. And I made sure that they both pass the test suite, but the second one is doing some more work that I want to show you to create something called an output graph. And I think it could be fun just to start off by looking at, let's copy solution 2 to graph.py, and let's run this on test input 1, and I'm going to use it with the -v option, and it's going to open up this graph for me, and it's going to show me what we saw here. If we look at the overlap here, 498, which you see 498 right here, could be joined to 442, and you see that branch right here. 498 joins to 442, but it could also be joined to 2391, which we see here, and then 2391 can be joined to 2323. And so that's really cool. Let's look at it on the second input. And I'm going to also use the -v option to open that for us. And you see here, it has created a much, much larger graph for us. And some interesting things to note here, right here, here are two sequences that join to each other, but they cannot be joined to anything else. And you see that there are a lot of different paths through this structure, and so we don't know which one of these is correct. And this will be the problem that you encounter with sequence assembly, is that just because it's computationally possible to join two sequences together doesn't mean that they actually in reality came from the same genomic region. So we have a lot of ambiguity in sequence overlap graphs. But that's part of what we're doing. We're just trying to get to the point where we can join these small sequences together into one larger or many possible larger structures. So that is very cool. How did I go about writing that? Well, let's look at what's going on here. The first thing is that when we run this, and let me just take this and just run this command as I show. And that's going to create an output file called one.txt. And let's look at one.txt. And we see here, and I show the output here, this is a simple text format that can be read by the dot tool. So it's using something called a digraph, which is a directed graph, and it is creating these nodes, and then it's saying that this node connects to this node connects to this node. So you could write this out yourself. It's very straightforward, but I'm using a module to write this for me. And so if we look at that program, solution 2, I am using the digraph from GraphViz. So GraphViz is the name of a Python module. It is not the same as the GraphViz program that needs to be installed. And I note in the book here that you may need to install that program. If you're on a Mac, you could probably use Brew to install it. If you're on a Linux platform, you could probably use apt or yum to install that. And this is separately a Python module that will, for instance, write that digraph format for us. And so let's go look at the code for that. All of this is exactly the same. Nothing has changed up here, but I have added this digraph function. by looking at the documentation, I figured out how to create this thing called a dot object. And in addition to all of this is the same, I find the intersections, but here when I do the star filter, instead of having something called pair, I'm unpacking that pair into S1 and S2, string 1, string 2, sequence 1, sequence 2. I print them, which is what the program needs to do, but then I additionally take each one of those and I create them individually as nodes. There's a node for sequence 1 and a node for sequence 2. And then I create between them an edge from sequence 1 to sequence 2. At this point, this part is what makes this function, this program pass the test. But there's one other thing that's going on here is that I use the dot render function, passing it the output file name. This is where I want the file to be written. And the view option is to whether or not to automatically open the file that is created. And that needs to be a Boolean value. args.view is going to be a Boolean value. If we go look at our args, it is an additional Boolean value. There's also an additional out file argument. And there are defaults for all of those. You notice that I didn't have to give them. So for the out file, you notice here for the argparse file type, I'm using a WT for writing. So I'm going to write something called by default graph.txt. So every time this function, this program runs, if I don't specify the output file, it's going to overwrite graph.txt, which is completely fine. And here is my view option. It is going to be a Boolean and it's going to use action store true. And so with these additional arguments, I have now written, I've now created a program that creates this huge overlap graph with actually quite not very much work by just adding 2 nodes for each sequence and then an edge between them. And you see how quickly this scales up to being able to create really pretty beautiful output. A couple notes here about graphs. One is that the graph that I created is directed. So if we run that again, we see that there are arrows here going from one to the other. That means it's directed. There's no particular reason why 144 goes to 2208. It could go the other way. I just happen to like to see the arrows, and so if I don't want those arrows, I could just have it to be a graph. If you have the arrows and there never creates a cycle, meaning that a sequence can come back to itself, then you're going to end up with something called a directed acyclic graph, which is very, very common in bioinformatics. And when I talk about the makefile appendix, essentially what a makefile creates is a DAG, a directed acyclic graph, of actions that need to be performed to transform one input to some output. And DAGs occur over and over again in bioinformatics. And so if you're not familiar with them, this is a great time to become familiar with them. If you have a cycle in your graph, that could point to a problem. Like if you have a linear genome, you probably should not have a cycle, but if you have a circular genome, maybe you do. Maybe that indicates that things went well. So DAGs are very interesting. They can point to problems or things that you're looking for. So if you're interested in this, there's something called De Bruijn graphs. I'm not positive that I'm saying that correctly, but those are very common. A lot of tools work on De Bruijn graphs, which are essentially overlaps. The way that we joined 2 sequences was rather simplistic. We were using very short k-mers, and we were looking for exact matches, and that is not that does not actually work very well in real-world data. We have a lot of times where there's ambiguity or sequencing errors, and then we have to account for that. And so you could, for instance, use your Hamming distance from the Hamming program that we wrote earlier to find sequences that have some allowable ambiguity between them. So a Hamming distance of 1 or 2 would allow for some sort of a variation there. And so I would encourage you to rewrite your program using that. And you would, of course, need to start off by eyeballing your data, creating some tests to ensure, given the small inputs that you have, that you're creating the kind of output that you want. So expand your test suite and then start expanding your program to try to allow for that. And, real world has to also account for inserts and deletes, which Hamming distance does not. And so you could, there's so many very interesting ways to take this further and to try to create an actual sequence assembler. So to review, I used the find k-mers function that I wrote to find the first and last k-mers, and when the k-mer size is greater than the sequence size, it continues to work because of the way that I wrote that function. I introduced the logging module that I think that you'll find useful when you're writing much larger programs, especially ones that need to run on a remote system, especially ones that need to run in parallel on many inputs. And you can easily log the output from each run to a different file. We brought back up the default dict, but this time using a different data type in there. Instead of int, this time we used list. So it creates it auto-vivifies the key and then with a default empty list value. We used a set intersection to find the common elements between two dictionaries. Then we used the product function from itertools to find all the possible pairs of sequences. And finally, we used star filter to find the ones that were not the same by importing the operator not equal. We went further with using the GraphViz tool to both represent our overlap graph. We really just wrote that to a file. So we didn't actually create in memory this larger graph. We just wrote it to file so that we could then use GraphViz to view it. So in a way, we sort of cheated there. We would have to create a much larger data structure, a much more complex data structure to handle the full assembly of that. And I would challenge you to think about how would you represent the full assembly in Python. We kind of cheated there because I found a very, very easy way to create this really pretty picture. But, how would you represent that in Python? We did it using the dot language, which was probably new to you. It's a very simple text format that even you could write just with Python, but I used the digraph module that helped to write it for me. And then finally, we just found that we could extend